All right, welcome. So with introductions to Hig. Hig is a geologist who lives in Seldovia and has spent his career studying tsunamis, earthquakes, and landslides. He received his PhD in geology from the University of Washington in Seattle and is currently focused on studying a landslide linked to climate change, including some that could generate dangerous tsunamis. He also helps organize Arctic TSLIP, a group of scientists and community members seeking to mitigate the impacts of landslide resulting from climate change. In addition to natural hazards, he has a passion for wilderness adventure, collaboration between stakeholder communities and scientists, trail building, natural resource policy, science communication, and chainsaw milling. Gottfried Hig, you grab the screen. Thank you.
Thank you, Anna. Um, yeah, no, I really appreciate you all joining me here today. Let's see, this is one of these things where Zoom puts something in the way, so I can't click on this. There we go. Yeah, I'm going to try exploring some of what I see as frontiers in deep-seated landslide risk. And I'm deliberately using the word risk rather than hazard. So this means like not only the physical phenomenon, but also how it impacts people. Just to give you a little bit of a roadmap, another way of kind of framing this is around a theme of deep-seated landslide science. I'm going to start out putting kind of looking at landslide risk mitigation as it compares to other areas of disaster science. To talk a little bit about quantifying probability and hopefully give you some sense of why I think this is a really important topic. About operational monitoring, so like actually measuring things and using that to respond to landslide risk. And then I'll dive into some of the physical science questions out there, both related to glacier retreat and to permafrost warming and how that influences landslides. And then I'm going to frame the end of my talk around this question: what should I do? And I'm not saying that the most important thing is what I do personally, but I kind of feel like I'm going to explain this sort of stuff. I want to explain why it is that I've chosen to focus where I put my energy, and hopefully that will be a framework that will be helpful to other people too. So there's an idea that I've stumbled across quite a few times in people talking about landslides, that maybe this is a sort of neglected area of science. This is one opinion piece in Scientific American, and it kind of argues that landslides are not studied that much by scientists, and it maybe is just because they're sort of boring. And I won't argue necessarily why they are understudied, but I will try to argue that they're not that boring. I thought I'd try to take a more systematic look at this question for this talk. So one of the things that distracted me from actually practicing it more was putting together this kind of funny table, and I'm going to add some pieces to it. But first of all, I wanted to figure out a somewhat objective way of looking at the actual problem itself, like how do landslides over on the right here compare to various other natural disasters. I kind of grouped it as things that might not only kill you but also destroy your home, so that kind of disaster. So I don't have pandemics up here, for instance. And there's a quite a lot of variation in how death toll has played out for different disasters. But landslide's certainly a pretty significant one. It's not as big as earthquakes and storms and tsunamis, but it's getting close there. In the U.S., actually, more death from landslides than from tsunamis on average. And if we look across some of the different topics that are parts of how we might mitigate this, these red patches over here are meant to denote sort of gaps in the work we've done. And I'll show you a little bit of how I built those. But before I do that, just to give you the overall pattern, I'm arguing here that we actually have quite a bit of progress on most of these different hazards, but landslides are a striking gap in what we've done. In order to put this together systematically, I went through and tried to break it down into a lot of different specific topics. I'm definitely not going to go into all of the detail of this, but I'd be happy to have a debate with anyone who wants to about the comparison of any 2 points on this graph. But overall, the message is, when I look around, I see a lot of really big gaps in our science and in how we use that science to mitigate these disasters. Now, I want to talk about one particular thing on this graph, and that's probabilistic hazard analysis. And so I circled these two. These are the big symbol means this is a relatively well-developed science with storms and earthquakes. We actually have quite sophisticated probabilistic hazard analysis, and that looks like this. So we have systematic mapping of earthquake hazards in Alaska, and actually in many places around the world, not everywhere, but a lot of places. And this is something where we estimate the likelihood that a certain strength of shaking would occur. This is then translated through building codes into mitigating action, and has been really successful in some cases. We also, everyone's probably familiar with, listening to a forecast, which will provide a probability that there is some certain storm or other condition, 50% chance of rain. It's kind of a frustrating forecast to get, but it's better than someone with a weather model is sort of worried about the weather tomorrow. So these are cases where we've really gone all the way through this process of developing probabilistic forecasts or estimates of a hazard. Now, if we look at landslides, you'll see things that look somewhat similar to this. And in particular, I'd point to the USGS's recently released map of landslide susceptibility throughout the US, including Alaska. Put a little crop of it down here. And so this is, I think, a really important step along this road. However, I think you'll find if you actually, take your particular home, if you live in the US and you go and you visit this map, that it's a little hard to see how it is that you would actually do something with this information. I'd also note that I've become a little bit negative about this word susceptibility. I feel like underlying this, the scientist who does the work to produce a susceptibility map, they probably have a probability in their mind that is describing what do I color red and what do I color green or whatever it might be. But that's not explicitly reported. It's not something that can be disproven through further science. And so it kind of obscures that topic. Now, what really got me started thinking about thinking that this problem of probability is really important was conversations I had with people up in the Glacier View area, and especially in this little neighborhood here where there's a Bible camp next to a couple lakes, and there's a neighborhood with a bunch of people that live down here. It's along the highway. This is Index Lake here. And we were worried about a few different things, and just to flag two of them. One is a landslide coming from up here that would be similar to these are landslides that happened in 2005 and 2006. If a landslide came from up here on the mountain, it could run all the way down, hit this lake, produce a tsunami, and this would be devastating for the Bible camp here and the neighborhood downstream. It could sever the highway. There could potentially be hundreds of people at risk. This is a really terrible scenario. Another thing that could happen here is that we have this rock glacier that's damming off this canyon. And so this makes it more likely that there would be a debris flow that would come from this area and flood down into potentially devastate this area here, could destroy homes and block the road and such. Now, if you come into this conversation, you ask, well, what's the worst that could happen? And even if we're only talking about those two things, the answer is very clearly this big landslide scenario with a tsunami and wider impact. If you ask what's most likely to happen, then it's definitely this here, and this debris flow risk. And so this presents a really, if you don't have a way of systematically comparing these things, the conversation can get derailed in either direction, and there's a temptation to ignore the other risk. We actually run into a similar issue when we look at in Homer. This is a map that's actually a serious attempt at mapping hazards in Homer. A somewhat joking sort of qualification of it, because I don't want to get in too much trouble by being specific about these things. But Homer has a couple areas of particularly high risk. Out here east of town, there's a bunch of canyons above where people live, and there's a risk of debris flows out of there. And west of town, there's a big deep-seated landslide that has a risk of retrogressively expanding and taking out the road here. And these are two, again, very different hazards that have different characteristics. So here's just an example of an August 2023 debris flow path that I visited. This one did some damage down when it reached the road. Here's an image of that big deep-seated landslide. You can see all of the infrastructure along the top. There's also a highway and a natural gas pipeline here. So I want to think for just a moment, like if we really got all of the details pinned down, what might those look like? We could look at a given risk with a curve like this, where we have on the y-axis an expression of probability, and on the x-axis impact. And as you go to, in this case, looking at higher impact scenarios, they get less and less likely. And so this would be what all of those canyon landslides might look like collectively. Now, you have a different curve when we look at the failure of this big landslide out west of Homer. And you can take and start just putting these together. You can actually add the two together and get a net probability. Now, this is not like I have all the data to pin down some of the details here, but the specificity is a real guess here. And when we're talking about this, we might highlight some specific scenarios. This is dominated by Bluff Point landslides. This is dominated by the debris flows east of Homer. But it is part of a continuous distribution of possible scenarios, including ones where, if you get way out here, maybe this is an earthquake triggered event, and both are a big contributor to it. Now, one of the things that's really valuable about taking and putting all this into one space is we can then ask about how do we prioritize risk, and this is something that there are a few jurisdictions in the world that have gone through and really systematically created kind of a context for looking at some of these things. So, for instance, in Norway, the red area here would be everything they consider high risk. Yellow is kind of intermediate, and green would be low risk. And so they would actually consider this situation in Homer quite high concern. Go for it, Joseph.
You're not showing a map right now to everybody.
It's not a map.
I can see it.
Okay. Yeah, no, it should be a graph, not a map.
I can't see anything except you. So I'll check my, sorry, keep going.
All right. If some of you have seen me talk about this stuff before, I've actually got a new graph here. I just found this one recently. It's based on risk assessment in Hong Kong, which has been used some in Canada. And they put almost everything in the space that I've defined here as considered high risk. This comes from people looking at landslide risk in the steep areas around Hong Kong. And this one I thought was really interesting because on my graph, actually I have to kind of squeeze it up to the right here in order to fit the graph that they use. They really look at much lower probability events than I'm typically used to. They have this area of intense scrutiny that I think that's an intriguing term here. That is actually way out in these very low probability but extremely high consequence events. Now, if we go to Switzerland, we get a completely different story. They actually focus in on some of the most likely Bluff Point failures as being most important. And so I see these things as ways of sort of talking about the spread of different landslide risks in a systematic way. And I would note that in some cases, I think it's hard to even start the conversation without being very careful about how we look at the combination of probability and consequence in this way. So this is Seward that you're seeing in the background, and there's this big crack in the mountain directly above Seward. So if this whole chunk of the mountain fell off and swept into Resurrection Bay, this is an apocalyptic scenario. I think if you just come out and you talk about that scenario without a lot of context, it's really reasonable for people to either just completely reject the conversation because it's kind of unimaginably terrible, or to be completely infuriated by those who completely rejected it. I think that if we were just to dive right in, it would be that conflict would be really naturally arise. However, if we can actually dive in and say, the question here is, what is the probability? Anything is possible, right? But what is the actual probability that something happens? We might find that, well, there is some risk here, and maybe this is something worth monitoring. Now, that brings us to the topic of monitoring, transition. When I've had conversations with community members about landslide risk, it's very often that we end up pretty quickly talking about monitoring, as in putting something in the mountains to measure the slope and hopefully detect something before it happens, or as we're getting close to a disaster. This is actually a pretty there's some history to this science when looking at very large landslides. There's actually a whole area of looking at how landslides move before they fail. In this example, it's actually one that didn't fail all the way. The top graph, it shows something that moved. It moved faster, and then it slowed down and stopped, and never failed catastrophically. But what people will use is they use a certain way of graphing it, where you get a line, and there's this prediction that when this line reaches 0, that's when catastrophic failure happens. In this case, about a half day before that predicted failure happened, the landslide briefly stopped, and then it went into a steady, slow sliding state, and it never failed catastrophically. But I can imagine watching this, and it would have been nice to have a heads up from this sort of instrument that something might happen. There are other more complicated approaches. I'm not going to even try to explain this, but I will note that someone wrote a paper where they compared black swans to dragon kings, which I think is pretty cool. So this is a whole a field of study looking at how instruments can measure something that might tell you that there's a landslide coming. Now, in order to understand this, you really don't have to try to figure out all the details in here. We might need to go actually to an area of earthquake science. It turns out that the way that friction is described in most introductory science classes, physics classes, actually doesn't describe a lot of real systems. And so that's what this whole block is on the left. It's basically describing a more complicated version of friction that seems to actually work pretty well for both things that you can do in the lab and also for real earthquakes. Now, an interesting detail here is we really don't scientifically understand why this is the case. So we have some math to describe it, but we don't actually have a explanation for it. And people who are working on understanding this, a lot of them have focused on the behavior of collections of grains. So this might be little crushed bits of rock that are in the sliding plane of an earthquake. The same sort of thing may be going on with landslides. And so this may be a promising direction to try to understand landslide behavior. One of the things that really, I guess, kind of blows my mind about this area is some of the documentation of landslides that have happened. I almost like the idea of looking at this graph without thinking about what the data shows specifically at all. I guess I've been watching some of these YouTube videos about astronomy and how they figure out, okay, there's a quasar going on, all these unimaginable, like, distant things, and the scientists actually constrain what's going on based on some very subtle signals. Now, if you were to look at this, we have some phenomena that happens here. We see these bright lines that show up. They're kind of sloping in different directions here. We've got a lot of organized behavior. this turns out these are tones. These are like vibrations that came out of this mountain in the minutes before it catastrophically failed. And this dark blue area is a period of relative quiet just before that failure. It's a lot of information, it's a lot of detail, and we see this repeated place to place, but we really do not know why this is happening. And there's really no explanation for this out there that really fits all these things together. So it promises a lot of potential improvement to our understanding of landslides in the future. So that's a little bit of motivation behind some of the instrumentation that's going on with landslides. I wanted to also spend a little bit of time trying to look at what we know about the different climate drivers for landslides. I won't talk much about how increased precipitation is driving landslides. This is probably the best studied area. It's actually a pretty interesting topic, but I think we kind of understand what's going on there. But I will look at glacial retreat. So this is the idea that some landslides might be related to glaciers thinning and the mountains next to those glaciers being less supported by the presence of that ice, and so they might fail. And also at permafrost. So permafrost in some cases may be an important part of the strength of a mountain. And so if you warm that permafrost, you could see a failure happen. I think we'll find that both of these have some very surprising patterns within them. So this is kind of a funny view. We're looking almost straight down. We've got a ridge in the foreground, and in the distance is a glacier down below it. And this ridge has failed. There was a big landslide on the right here. There's actually boulders bouncing down the slope as I took this photo. But you also see all of these cracks here in the mountain. And plausibly, there's this landslide, the cracking is related to the thinning of this glacier. But that's sort of surprising, right? The glacier is way down there. How does the rock up here end up falling apart and breaking due to something that's changing down at the bottom of the slope? So the explanation that's usually looked to here is what I've usually called static buttressing. And so I've also sometimes called it slush bucket buttressing. So the idea is that you have ice and water in the glacier. And the ice actually, the ice is thicker than the water part, and the water permeates the mountainside. So this is the water, it sticks out here. And so at any given point, you have some combination of the weight of the ice pressing against the slope and the buoyant effect of the water that lifts the ice and reduces that pressing force. And so the amount of pressure increases until you get down to the water table and then decreases. And in this case, I have it going to 0 at the bottom, which implies that the water is basically as deep as it can possibly get within the glacier. Commonly, this wouldn't quite be the case, but it's a simple case to look at. Now, you can use a model like this, and you can see that if you thin the glacier, that you reduce the amount of force. So basically here it was before, the area is reduced as I go down. That's basically all you need to get out of this graph, is that as the glacier thins, you have less total force acting here. Now, that's I think what a lot of scientists picture when they talk about debuttressing. However, there's another scenario that we can look at. Instead of thinning the glacier, what if we just drop the water table a little bit? So here's the original curve here, the dashed line. If you drop the water table a little bit, then you get this huge increase in the buttressing force. So you can see that there's these two competing factors. There's the water table and there's the ice thickness. It makes the prediction that a lot of people would assume that if you thin the glacier, then the buttressing force decreases. But it also says that there would be this increase in buttressing if water table decreases. One reason why water table might decrease is that the glacier might retreat. So that the ice front being closer gives you better drainage of the water. And so then you would see an increase in buttressing forces. So the prediction this makes is that ice thinning would reduce the support for a mountainside, but glacial retreat would increase the support. So these are two competing processes that both happen during overall glacier thinning processes. Now, all of that is a static view of glaciers. Real glacier got flow. So we've got a whole lot of other things going on in here that are not included in that model at all. And as far as I know, these are not being actively described right now at all. Okay, I've already spent a lot of time, and I do really want to talk about permafrost. Permafrost, it turns out, presents a lot of very interesting challenges. When I started learning about permafrost, I thought of it in this way, with kind of this one-dimensional graph. So over here we have depth, and then we have temperature. For some reason, I'm mixing English and SI units. Apologies for that. If you go from the average temperature at the surface, you'll see it increase downwards in a steady state climate. So it tends to increase linearly if there's constant insolation. And during a given year, the temperature will vary a lot. That's this blue range up here. But that variation will decrease with depth, and at some depth, it basically comes to be constant. Now, because things have been warming over the last couple centuries, we see these curves kind of tilt over. So we have a shifted temperature behavior at the surface, but the lower part has actually no idea that these changes have happened because that heat hasn't yet conducted to these deeper depths. Now, a lot of what people think about with permafrost and landslides is permafrost thaw. But thaw is only happening in this tiny little sliver at the top here. And if we look at real landslides, we'll often see phenomena like this. So notice there are these weird piles of rubble here next to these boulders that are about 10 meters, 30 feet or so in diameter. So these are giant boulders. They're kind of too big to be all above the permafrost anyway. And we also see these boulders that have crumbled into gravel. So this indicates that the failure that produced this landslide was actually below the permafrost. And we can see an example here from a different landslide where right after the landslide, this boulder slid out here, and you can see a big round boulder, but then in time, the permafrost in it melted. So if we use this really simple model, we don't predict anything like that because we would be looking only at if we're looking only at that thaw up here, we've got a failure that's actually incorporating some of this intact permafrost deeper down. We see other kind of strange patterns in permafrost. This is actually a graph I took from a colleague, a grad student, King-Yu Sui, who presented this just a couple days ago. And the only important thing I want you to get from this is this kind of stair-step pattern in some of these permafrost landslides. They're called rock glaciers, but I'm going to call them landslides for now. There isn't really a strong distinction. And this is seasonal behavior. So what we're seeing is that the landslide slides along constantly during the summer, then it basically stops over the winter, slides, stops, slides, stops. So this is actually a really surprising pattern because where this sliding is happening is too deep for it to be explained by simple conduction from the surface. So too deep to be explained by this way of thinking about it. One more thing that I think adds some sort of confounding observations to this is that we see a number of places where we have large masses that are suddenly accelerating in just the past decade or so and moving down slope. Now, so this one here is failing somewhere well over 100 meters below the surface, maybe close to 200 meters down. So it's below most of it's below the warming that we would predict since the Little Ice Age. And this is not the exception. This is a big one, but there are other really big ones. This one, again, we'll see the several years where nothing's going on. And then at the end of this sequence, you'll see this part start moving and then the landslide propagate down towards the valley. This specific spot, which I call Dietrich River D up by Adigan Pass, is an interesting case. This picture was taken yesterday. Here's the toe of the landslide here down in the canyon. There's only 12 meters here left before it's going to reach the other side of the canyon. And it's moving somewhere on the order of 50 meters per year. So we expect sometime in the next few months that it's going to actually close off this canyon. And this is just a few miles upstream of the Trans-Alaska Pipeline and the Dalton Highway. So there's some risk of a dam leading to a flood here. So one idea that might explain some of this is the idea of strain heating. It's sometimes called a creep instability, not so much in landslide science, but that's actually ice sheet dynamics, so like studying places like Greenland. And the idea there is that if something does start moving, that it might, that the actual motion could heat up the permafrost and thus weaken it. Okay, I jumped around through a lot of things. Those are some challenging bits. I do want to ask this question: what should I do? And again, I'm saying, what do I do? This isn't that I'm trying to keep it all about me, but I want to try to explain why I've focused where I have. And part of that focus, or part of my decision-making process there is I've tried to figure out what is the standard I have for succeeding. And I try to make that standard as objective as possible. And I think the standard that I would like to apply to myself is that when something happens, I want to be able to look back and say, did I do some things that actually made the situation better? And the reason I focus on that is that I think it's really easy to focus on a lot of other sort of indirect measures, but ultimately this really difficult problem of hazard mitigation, and that ultimately is the goal, is that we would actually do something that we would, when disaster struck, decide was useful. So to illustrate that, I'm going to show two different examples from just last year. I had been speaking with some folks at a lodge west of Seward about tsunami risk because there was a tsunami near their lodge from a landslide in 2022. And on August 7th, they gave me a call and they said, hey, something happened. This is a rack line, so a drift line from a wave that went into the forest here, not far from the lodge. There was some minor damage, and they said, they had no visibility. It was raining hard, but they said, we think there might've been something that happened like what I was talking about. And it turned out there had been a landslide up in the mountains behind the lodge. So landslide came from here, and it went down onto this glacier, slid down, went into this lagoon, and produced a tsunami. The lodge is over here. So the tsunami swept down through here. If you go up into this area, you can see the impacts of this. This is forest that was completely swept clean by that tsunami. You can walk around and see alder forest flattened and buried in gravel. Later, I got a chance to go out and measure the height that the tsunami reached in various places. So up to 62 meters, which is over 200 feet up the mountainside. Fortunately, by the time it got to the lodge, it was quite a bit diminished. And so this, to me, is a case where one of my tests, I was tested as far as the work I'd done. I would say a small amount of success here. I was able to be engaged with them right after this disaster, as the lodge personnel made some difficult choices about how to respond to the situation with guests on site and so on. And I hope that was useful. It was fortunately not a deadly event. If I had done nothing, it wouldn't have been that much worse. So I see it as only a very small success, but it's an example of how I can make this objective measure. One other example where I would say I don't get any gold stars this time was a landslide that happened in June last year. And so you can see here it's sticking out into the Clutina River. This landslide is in an area that I've been doing some mapping in after a local told me about some landslides that had happened previously. But it was all just some stuff on my computer. I hadn't really talked to anyone about it. And so this landslide happened in June, and then a month later, there was a guided rafting party coming down the river. They hit the end of this landslide, probably caught by surprise, thinking they knew the river. The raft capsized, and one woman died and drowned in the river. So this is something where I can conceive of how I might have been valuable, but despite having worked in this area, there was no actual value that came out of that work before this disaster happened. Okay, so what do I actually do about this sort of thing? One thing I'm doing is I'm really trying to understand what's going on out there. I'm doing a lot of mapping of different sites where there is activity in Alaska. There are a lot of different ways you can slice and dice this information, and happy to talk about those. But an example would be trying to pick subsets of sites where that we could use to estimate the likelihood of failure in a given location. So this is a large number of slow landslides I've mapped. If I start paring these down to ones, paring this down to ones that have properties similar to a certain site here. So we're going to go down to slow landslides, and then slow landslide, or slow, relatively fast moving slow landslides near glaciers without permafrost. This would then describe both the site at Portage and at Barry Arm. And then we can look around the state and see how many of these failed in a given time, which turns out to be about 5 sites. So we can make an estimate of the likelihood that any one of these fails in a given year, which ends up being about 0.5%. There's some reasons, including that they seem to be increasing in frequency, that this is probably a low estimate. It might be more like 1% or something like that per year. So this is one approach that I'm working on. Another, I've been really engaged in advocating for workshops to start conversations with locals to understand hazards and to see what we can do about it. And I think a key aspect of this, where I've really focused in, is on translating a local interest in landslide hazards into some level of locally owned monitoring. And so I'm actually working on these pretty goofy looking little instruments that are instruments to monitor landslide motion, designed to be as cheap as possible. I think my colleague John McGinnis is on the call here, and he deserves a lot of most of the credit really for coming up with the idea of how to put these together. The instrument I just showed you is right here, strapped to this tree. And it's shooting to a reflector here. It's a little radar signal, measures distance, and so we can see the motion of these boulders are on a landslide. And part of the whole idea here is to have that instrumentation owned by the community, and in order to solve some of the challenges of these instrumentation systems. All right, my last note I want to make is to circle back to permafrost. I've increasingly been wanting to focus on permafrost phenomena, partly because I see some sites where this is a really big hazard, and partly because it's a particularly huge hole in our understanding. And I wanted to just note the range of different hypotheses as to how you would get these failures that are happening below the surface, below the active layer, so well into the permafrost. I think a lot of people initially think about talus, which are holes in the permafrost under the ground, and also three-dimensional heat flow in ridges. These are definitely plausible and plausibly important processes, but I want to note they're not the only one out there. I mentioned shear heating, so that if you have some deformation happening, that might warm things up and lead to an increasing rate of deformation. We also have all of the ice segregation processes, things we call frost heave. This may be an explanation for that seasonality we see in rock glaciers and other slow landslides. It may also be things as simple as just the full three-dimensional view of a landslide. Even though the base is really deep, the margins are not. So the margins are really sensitive to surface changes. We might, when we look at a moving landslide, one of the processes that's seems to be important is that you'll get dilation of the material. And if you have permafrost, then you have the potential to fill void spaces with ice and prevent them from collapsing again. So this could substantially change the dynamics of these landslides. We could go further, freezing point excursion. So basically, if you overpressurize ice, it actually melts at a lower temperature. So if often when you have moving rock mass, it leads to these high pressure points within the rock. So big picture, looking at this long list, there's a lot of very complicated dynamics that may or may not be going on in these landslides. And it's going to be a lot of work in order to understand which of those are important. And just to leave you with one last image. So on the right here, we have these huge cracks above a glacier. This is an upper trib of the Klutlan Glacier. And I think it's an interesting case. We'll see that landslide develop right here, because it's one of the best examples where we have both these glacier and very likely permafrost processes happening synchronously. Okay. Anyway, I apologize for that being a little bit of a leap all over the place kind of presentation. And I did talk a little bit longer than I wanted, so I'm going to stop there, and I would love to chat about any of these topics.